before we touch a single component, I want to talk about what Felix actually needs to work. At its core, any robot needs three things. First, a brain. Second, motion. Third, senses. Something to think, to make decisions, to run the logic that controls everything else. Motors to move, drivers to control them, and an algorithm called PID to make sure that Felix moves accurately, not just randomly. Ways to understand the world around him. Line sensors, distance sensors, whatever Felix needs to react to his environment. Okay, so we got brain, motion, and senses. That's the whole robot. This episode, we're starting right here, the brain. And right now, it's a question mark. Meet the PICkit18F46K22. Before we touch anything, let me explain to you exactly what this is. Because if you're coming from Arduino, it's going to feel familiar, but it's different in a really important way. A microcontroller is a complete computer on a single chip. It has a processor, memory, and a bunch of input and output pins all in one package. When you power it up, it runs whatever program you have flashed onto it. That's it. No operating system, no file system. Just your code running directly on the hardware. Now you might be thinking, isn't that what Arduino is? And yes, sorta. Arduino uses a microcontroller too. But Arduino wraps it all up in layers of software and pre-built circuitries that hide all the complexities. What we're doing with Felix is working with the chip directly. No wrapper, no safety net. So why the PICkit18F46K22? Now that we actually got the chip, let me explain more specifically why we're using this chip. Felix needs to control 4 motors simultaneously. This chip has enough PWM channels to handle that. As I mentioned before, we're going to be using PID to control the motors. This chip has enough memory and timers to handle that properly. It's also got hardware UART, I2C, and SPI built in. That means I can talk to sensors, Bluetooth modules, and other peripherals without having to hack it together in the software. And it also comes with a DIP40 package, which means I can fit it right into the breadboard. Perfect for where we are at right now. Alrighty, let's actually build this thing. The minimum circuit to get this thing running has a few key parts. First, power. Pins 11 and 32 need 5 volts, and pins 12 and 31 need ground. And right next to each of those pairs of pins, we add a 0.1 microfarad decoupling capacitor. These absorb tiny voltage spikes and keep the chip stable. You'll see this basically on every microcontroller circuit ever made. Next, MCLR, that's pin 1, and it's the reset pin. It needs to be held high for the chip to run. So we put a 10K resistor from pin 1 to VDD. If MCLR ever gets pulled to low, the chip resets. That's actually how the PIC4 resets it to get into programming mode. Now the clock. This chip needs to know how fast to run. We're giving it an external 20 megahertz crystal. This crystal goes between OSC1 and OSC2. That's pins 13 and 14. And each of those pins get a 22 picofarad capacitor to ground. Those load capacitors are part of the oscillator circuit. Without them, the crystal either won't start or it'll run at the wrong frequency. And finally, the 3 LEDs, red on RDO, green on RD1, and yellow on RD2. Each one of those get a 330 ohm resistor in series to limit the circuit, cathode to ground. Also, a reset button between pin 1 and ground so that we can restart the chip at any time. Now that's the whole circuit. Let me do a quick sanity check before we plug anything in. Circuit's wired. Now let's write the code. I've got MPLAB X and the XC8 compiler installed. The links are in the description if you need them, and both are free from Microchip. We're going to create a new project. It's going to be a standalone project. The family is the PIC18. Device, PIC18F46K22. The tool we'll use is the PICkit 4. The compiler is the XC8. The first thing you'll notice is the config bits at the top. These tell the chip how to start up. The important ones here are FOSC. I'm setting that to HSMP, which means use the external crystal in a high-speed mode. And MCLRE set to EXT MCLR, which means use the MCLR pin, which matches the pull-up we just wired. Then we'll set the clock frequency for the delay functions. 20 million, because our 20 megahertz crystal. In main, we set the 3 pins as outputs using the TRISD register. 0 means output. Then we go into an infinite loop and just toggle the LEDs. This part here handles the sequence. Red on, wait, red off. Green on, wait, green off. Yellow on, wait, yellow off. Then all 3 on together, then all off. Half a second each. Simple, but this is the first code this chip has ever run. Alrighty, now that the code's done, we can flash the chip. The PICkit 4 connects to the 5 pins on the chip: VDD, ground, MCLR, PGD, and PGC, which are the data and clock pins. I'm using some jumper wires from the programmer header straight to the breadboard. In MPLAB, hit the run button. It'll compile the code, connect to the PICkit, and flash it automatically. There it is. That's the code I wrote, running on a circuit I built, on a chip I wired up from scratch. No Arduino, no module, no magic, just a chip doing exactly what I told it to do. That was exciting. Now I know a blinking LED isn't going to win any robotics competitions out there, but this is a foundation for everything else to build on. The chip is alive, the programmer works, the clock is running. From here, we can add anything. In the next episode, we're going to add a motor driver. We're going to wire it up, write some control motor code, and get a wheel spinning for the first time. See you in episode 3.